Hello, Dangal greetings. My name is Siron Vinsnovi Corminal of 2CSC, and this is our explanation for the main of code in the task to design and implement the Smart City Emergency Response Management System, which relies on custom graph and binary search tree data structures. Starting on line 5 to line 12, public static void main and the data structure initiation defines the program's entry point and initialize the core custom data structures. The scanner for the input, the graph for the city network or F2, and the emergency BST or so-called emergency binary search tree for prioritizing cases or so-called F1. Moving on to line 14 to line 20, final string respond are RSP ambulance. Declares constant string variables for responder types and emergency prefixes, ensuring consistency in logic and output, which are the constants. In line 22 to 30, tree insert method preloads 9 initial dummy emergencies into the binary search tree where they are automatically organized by the urgency rating. F1 prioritization. Then, moving on to line 31 to 40, graph.addLocation method and the graph.addRoute method builds a city map by adding 5 key location as vertices and 5 weighted routes as edges, defining the road network and distance. Roadwork ne- Defining the road network distances. F2 graph modeling. Now moving on to the line 41 to 43, the graph add responder to method allocates the three initial emergency units, the ambulance, fire truck, police unit, to their starting location on the map, which are the F3 unit allocation. Now, moving on to the line 46 to line 59, while run, loop, and the switch chose. It established the continuous main menu loop, prints the 7 core options, and uses a try-catch block for robust input, reading and error handling, which is the user interface. Now, moving on to line 61 to 68. Case 0 break. This handles the exit command by setting the run flag to false, ensuring the clean program termination. It is the exit logic. Now, moving on to line 69 to 104. Case 1, manage location. Allows the user to manually add new location. Graph, which is the graph add location method, and define new routes, which is the graph add route method, dynamically modifying the city graph. This is the graph management. Now moving on to line 105 to 129. Case 2, manage responders. It implements the features F3 by allowing the users to add new units, which is the add responder to method, to existing location after validating the responder type. This is the unit allocation or the F3. Then moving on to line 130 to 134. Case 3, manage emergency case. This delegate control to tree.run menu method, which opens the binary search trees dedicated menu for creating, searching, and deleting emergency cases. This is F1 or the binary structured. This is F1, the binary search tree management. Lastly, This is line 5, and lastly, in line 135 to 139, case 4, visualize. Calls graph.display method, which prints the current state of the city network, showing all locations and connections. This is F4, which is visualization.
So hello the mga greetings. By the way, I'm Christopher M. Zarate from 2SC. I'll be reporting the main of our code. So lines, code block, summary, explanation, features, integration. Line 142 to line 151. Priority retrieves and alert. Retrieves the absolute highest priority case using three primus urgent and print the essential details. Type, location, urgency. As an alert, F6, F1, F6. Line 155 for dispatch, call F4. Calls the graph, find the nearest available responder, which execute the find the shortest path from the nearest available unit to the incident location. F4 dispatch optimization. Line 157, line 166, on-site or failure logic. Check in the unit already at the location, distance equal to 0. If so, the case is resolved and deleted immediately, handles failure is no unit is available. Control flow. Line 156 to line 174, path retrieval output retrieves the shortest path array, the shortest path result object, and print the final result, the optimal responder found in total travel distance, F4 output. Line 176, line 185, visualization loop setup begins the loop to draw the route, check the current index I to assign start and incident status marker for the ASCII. Visualization F5, F5, status markers. To line 187 to line 194, path segment drawing. Inside the loop, grab get route distance, retrieve the specific weight distance between 2 points, and print the ASCII graphic for that segment. Line 196 to line 107, resolution. Once the visualization is complete, deleted by urgent and type, removes the resolved case from the BST step 9, F1 resolution. For line 207 to line 213, summary report, execute feature F7 by first calling graph display for the city's city map status, and then for filming a tree and other traversal to list all remaining active emergency cases ranked by urgency. Line 215 to line 220, default invalid choice. Catches valid integers entered by user that do not match a menu option. Line 222 to line 227, catch input mismatch exception. The final error handler, the main loop, catching non-integer input, example text, to prevent a program crash ensuring robustness. To line 230, input close, closes the scanner resources concluding program cleaning. And that's all for the main. The next function will be explained by the other member.
Dangal greetings, I am Alex Kate and I will be explaining the vertex part of our graph. Let's proceed. First, in lines 3 to 9, we have the attributes. These lines define the core properties of a location or vertex. This includes the name of the location, the list of responders like ambulance, and an array edge objects that stores the route going to neighboring vertices. This is part of feature 2 graph node. Next, under the line 11 to 14, we have the constructor. This initializes a new vertex using the given name. It also creates the empty arrays for edges and responders so the vertex can store routes and emergency units. This falls under the initialization part of the code. Moving on to the line 16 to 25, we have adjacency, also called add route. This handles adding a new route from this location to another vertex. It also checks if the edges array is full and resizes it when needed before inserting the new edge. This belongs to feature 2, edge management. After that, in lines 27 to 37, we have add responder. This is part of feature 3, unit allocation. It handles adding a new emergency unit to this location. The method includes a safety check if the responder array is full. It automatically resizes resizes it. Then it adds the new responder and updates the responder count. Finally, in lines 43 to 56, we have the getters. These public methods allows us to retrieve the vertex name, all responders, the responders count, all edges, and the number of edges. This is part of data access. And that's all for the vertex section of our graph. The next part will be explained by the other member.
Initialize the list object. It creates a new vertex array with the initial size of 1 and set of elements count size to 0. This method implements the dynamic resizing logic for the custom array. It's checked if the current array size is equal to array capacity vertices dot then it full. It creates a temporary array temp with double the capacity. Cap it copies all existing elements and updates the vertices and the reference to the large array. After checking
Tangal greetings. My name is Rochelle Francine Manrique. This code is purpose is edge for the graph. For line 4 to 7, class attributes defines the two essential private fields of a weighted edge. Private in distance, the weight or cost of the route in kilometers, and private vertex neighbors, the destination location or vertex in these routes connects to. Line 9 to line 12, or the constructor initialize a new edge object. It accepts the destination vertex neighbors and the distance weight and assigns them to object attributes. Line 14 to line 19, the setter methods provides methods to change the destination vertex, set neighbors, and update the route's distance set after the edge has been created. For line 21 to line 26, the getter method provides public access to the edge information, get neighbors, returns the destination vertex object, and get distance returns the route's weight distance in kilometers. And that's all. We have explained the function for the graph to needed code to work, and next will be the graph, the logic behind all the codes function in. Graph it will explained by Bill Santa as the person who designed the graph.
Dangal greetings, my name is Tyron James Materials from 2CSE, and I will be explaining the Node Java class that represents a single emergency case that is stored and managed within the emergency BST for prioritization. Within the line 4 and line 9, the class attributes. This defines the four essential private fields of an emergency case node type, such as example, fire, fire and medical, location, the incident site, urgency, the priority level, example 1 to 10, and pointers for the left, emergency node left, and right, emergency node right. Children which maintain the BST structure. Within the line 10, line 14 constructor, this initializes a new node emergency case with its type, location, and urgency. It also sets the left and right child pointers to null, as a new node is always initially a leaf. In the line 16 and line 23 getter methods, this provides methods to retrieve the type, location, and urgency of the emergency case. These are used when the system selects the most urgent case for simulations, F1. In the line 24 and line 42, the setter methods, this provides methods to update the case attributes such as set type, set location, and set urgency. Additionally, it includes setters to link the node to itself, its left and right children, which are used during insertion and deletion within the emergency BST. In the line 44 and line 49, the child getters, This provides method to retrieve the node's emergency node left and emergency node right children, which are essential for traversing and balancing the BST. That's all for the binary tree. The next reporter will explain the emergency BST to explain the code by Palarao as person who designed the binary tree. And thank you.
Dangal greetings. I am Jinja Sierra Palarov, the one who designed for binary tree emergency TBST for our group project. Okay, let's proceed. For line 1 to line 4, define package import scanner, utility, and input mismatch exemption for import handling and declares the main class emergency BST. For line 6 to line 9, declare the core private field route starting to node BIST to count to track of number of use for displaying indexing choice and location and type, and public void reset count utility reset back to 1, and public void insert for line 13 to 16 the public wrapper methods that call private recursive insert rec perform to the BST insertion. And for line 17 to 27, the private node inserts recursive insertion to method to checks for the null base case for L18 to line 21. Then the recursive traverse the tree based on the new urgency value of line 22 to 26. For line 29 to 30, public node search. A public wrapper that method that calls a private recursive to search rec starting from the root. And the private node search rec recursive search method to handle two base case not found to line 33 to line 35 if found. If recursive traverse left or the right based on the urgency comparison for line 38 to line 41. For 43 and line 44, public node delete by urgency and type. A public wrapper methods that calls complex private recursive deleted rec to resolve the emergency. For line 46 to line 73, the private node delete tree. A recursive deleted method that handles base case line 47 to find correct node via traversal line 49 to line 59 and implement the three main deletion cases of no one or two children for line 60 to line 70. It uses find meet for the set two child case. For line 75 to line 79, private node find meet. A helper method to use with delete rec to traverse the left or given to define the in order successor to minimum value in the right sub tree. The public node most urgent. Public wrapper method that calls private recursive helper to find the most urgent. For line 85 to line 92, the private node find most urgent rec recursively iterate to traverse the right to sub 3, while that node get emergency node right and to find the right node which is hold the maximum urgency. Then to line 94 to line 101, the public void in order. Recursive in order traversal to method to use for display it recursively visit the left child to line 96 to print the current data in the line 99. Now, for 103, public node get truth. The method is return truth BST, often useful to pass the tree traversal to function the in order. For line 105 to 109, the public void run menu setup. Define dedicated menu method for BST management initializes the local scanner and control the loop. For line 11 to line 12, menu display. The print main option insert display, search, top priority, delete, and use to try catch for robust input handling. For line 22 to line 26, case 0, it's an exit menu to run the loop and returns to control to main Java or to the graph. For line 27 to line 150, case 1 insert emergency. Handle user input for the type location urgency includes for essential validation loop to line 135 to 147 to ensure the urgency. Now, for case 2, display emergency. It prints the emergency in the sorted by urgency reset counts the call 3 in order to get the truth. To start the traversal in display. And case 3, to search emergency for prompts for urgency to label calls 3 search and prints the details and first matching case found or print not found. Case point. The find the top priority. It calls E3 find most urgent to find display the emergency with the highest urgency rating. And case 5 to delete mark emergency that has been solved. Proper urgency type and calls the deletion of urgency and remove the case and confirmation of removal. Default. For handle the invalid integer inputs choices to other than 0 or 5. And catch input is a handle a non-integer input gradually in present error clear input for buffer if next line to prevent infinite loop. And that's all for the binary tree BST for our group project, and other function will be explained for other group members. And that's all. And thank you.
My name is John Posible Santa, and today I will explain the graph design of the Smart City Emergency Response Management System, or SCERMS. I will explain every function inside the graph, and then we will proceed. Line 6 to line 33. Public boolean, add responder, string, location name, string, responder. This method handles features to F2, add resources to a location. Line 15 to 19. Find location check. It first use location, find location from line 95 in graph Java. To ensure the destination name exists, if it doesn't, it returns false. Line 21 to 28. Responder list check. It iterates to the existing responder array of the targeted vertex. If an empty slot is found, it calls vertex add responder from line 25 to add a new unit. Example, fire truck F01. Line 34 to 47. Public boolean add location string location name. This method handles features F2 add location to the map. Line 40 to 43. Find location check. It checks the location name already exists. If find location name is not null, the location is already on the map, and if it return false. Line 44 to 46. Vertex creation. If validation passes, a new vertex object is created and added to the vertex list. Line 48 to 73. Public boolean add route. This method handles features F2 connect location, add weight edges. Line 50 to 55. Location check. It validates that both N1 and N2 exist on the map using find location. If either is missing, it returns false. Line 56 to 59. Self-route check. It ensures location cannot be routed to itself. Check if L1 and L2 is equal to one another. Line 60 to 66. Duplicate check. It iterates to the edge of the starting location L1 get edge count to confirm the route doesn't already exist, preventing duplicate connection. Line 67 to 69. L1 dot add edge. It checks if all checks pass. It calls L1 dot add edge and L2 dot add edge to create a bidirectional between the two locations with the specific distance. Line 75 to line 93. Public void display. This method executes the city map status display part of pictures F7 summary report. Line 75 to 79. Location info. It iterates to all location and prints the location number and name. Line 80 to 85. Neighbors loop. It loops through the edge and array of the current vertex, printing the name of each neighbor's location and the distance to it. Responders loop. It loops through the responders array of the current vertex, listing all available emergency unit mentioned at the location. Okay, so before I proceed explaining the remaining code function, Pilar will explain the important function of roaming code.
Thank you, Billy Santa, for giving me time to explain the helper method. The shortest result Java component explanation. The shortest Java class is helper object to use the package and transfer the final validated result to dispatch the optimization algorithm for feature F4. Its sole purpose to serve is a clean, standardized container for optimal solution and calculated by graph and method, and to find the nearest available responder. Now, for line 4 to line 7, attributes. It stored the incident essential data to start location where the optimal unit was found and location, the inside, the total distance, the calculated shortest distance kilometer, and path location. An array string of listing of location optimal sequence for use for visualization. Now, for line 9 to line 13, initialize the result object to take 4 critical pairs of data to calculated by the graph class start, lookup, and lock this path and assign them to object attributes. For line 15 to line 23, getters, the public method to retrieve the start location, end location, total distance, and the path location for array. Now, that's all for helper method. Thank you, Billy Santa. You may continue to explain the remaining for the graph.
For basic input validation and by all other methods requiring a vertex object, examples are add route, add responders, and shortest path. For line 106 and to 113, public vertex find responder, string responder. It's the same function as public vertex find location name, string location name. It is a helper function that attempts to find a location based on a responder's name. It currently duplicates the find location names logic, but it is intended for a more complex features. Line 121 to 138, public int get route distance string. The same as the other two, but this method retrieves the direct distance between two connected locations. If find the starting location lock 1 and iterates through the edge to find the neighbor lock 2. Return the edge distance. This is used by main Java for the find visualization or F1 display. In line 188. Now, for our array initialization. In line 143 to 146, it initialized the core data structure distance, stores the minimum distance found so far for each vertex, predecessors store the previous vertex of the shortest path and visit a boolean array to mark finalized vertices. Start and end index from line 148 to 160. It iterates to the find array indices, start index and end index corresponding to the input location name. All distance value are initialized to integer max value. Start distance. The distance that starting location is set to 0 to begin the search. That is line 165. Now, from line 167 to 182, find the minimum. The main loop runs until all vertices are processed inside it. It finds the unvisited vertex with the current smallest distance value. This index becomes the mean distance index. Line 183 to 203. This section performs the core relaxation step. The shortest path update, it iterates through all edge u dot get edge of the selected miss distance index vertex. Line 19 to 200. Distance check. It checks if a short path to a neighbor, a B target index, is found. If true, the distance B target is updated and the precedenter is set to mean distance index. Line 99 to 200. Distance check. It checks if a shortest path is to the neighbor. B target index is found. Distance mean index plus edge dot get distance is less than distance B target index. If true, the distance B target is updated and the precedenter is set to mean distance index. Line 208 to 209 and check if the distance to the end location is still integer max value. It means the location is unreached and the function returns null. Line 212 to 228. Fat reconstruction. Using the precedenter array, it backtracks from the end index to start index to reconstruct the sequence of location, the path. The path is stored in the final path array. Line 229, return value. The final optimal route is packed into the shortest path result object and return containing the start and end location, total distance, and the path sequence. Shortest test retort find available responder string indices name. L line 232 to line 256. The dispatch optimization method. It iterates to every location vertex in the graph. Line 242. It checks the two conditions for each location. 1. Does it have an available responder? Get responder count is greater than 0. Line 245. 2 is the path from the location to the incident shorter than the current shortest path found. Line 249 to 250. It returns the optimal best route. And that is all for the graph. Next will be the video demonstration of the code on how it works.